me show you something from yesterday. Given enough time and enough depth, what's going to happen to the sediments? What's going to happen here, Julissa?
It's going to become cemented.
That's good. Now, how are you going to spot, how are you going to identify sedimentary rock when you see it? What's that?
You have deposition.
Well, you're telling us, Shauna, how it's made.
Yeah.
And, you know, that's certainly a good thing, all right? But I just want to come back to this.
Yeah.
You know, we know how it's made. Sediments get deposited and buried and cemented together, as Julissa tells us, and it forms sedimentary rock. But my question is, how are you going to spot it? How are you going to identify it when you see it? There's a lot of roads that are cut through sedimentary rock, and you can see it if you know what to look for. What's that, Stephen?
When it certain rocks might have layers on it.
Oh.
What?
Let's see. Like that? Now, how do you know that's sedimentary rock? How do you know? How do you know? How do you know, Natasha? Look at it. How do you know it's stuck together? Oh, say that. Okay, that's what, who said that? That's what Stephen said. Absolutely. Absolutely. So, you know, just in a cross section, looking at it from the side, it appears like that. All right, now, why do you suppose you can see the layers here? Because if this river wasn't here, you wouldn't see the layers. What did the river do to the rock? At least the sedimentary rock. What's happening here, Courtney?
They have different kind of man-made stratus.
That's good. You know, the word, that's a good word. Another word for layers are strata. Okay, but what did the river do to the sedimentary rock? We did this. What is that, Edgar?
It cuts into it.
That's right. So here's a wonderful example of a river, the Colorado River, cutting a canyon. And in canyons, if the river is cutting through sedimentary rock, you can see the layer. Now let me ask you this. Suppose, and this was our little model for yesterday, suppose when the sediments got deposited in some ancient sea. Sorry. Suppose an animal, the remains of an animal, got deposited in the river along with the sediments. So now we have an animal, you know, that could have been buried a million years ago, 10 million years ago, 50 million years ago. What do you think's going to happen to that animal? Randy, what do you think?
It's going to blend into the rocks with the rest of the sediments.
That's right. Now there's a word for that. There's a word for that. What's that, Cherise?
Becomes fossilized.
That's good. Very good. I'd love to pass it around, but since it's sedimentary rock, you can see the layers here. I'm afraid that it's going to fall down and crack. So I'll just come around. How do you like that, Tyrone? Huh? You did good yesterday, Akil. All right, now let me ask you another question. Suppose we dig down further into the sedimentary rock, into a layer that's underneath it. Maybe this fossil of a fish is found in here, and maybe something like this is found below it. Well, it's called a brachiopod. And to us, it looks like a clam. And it's a shelled animal. If you had this fossil and you found it over here, which would you say is older? Which would you say is older? What would you say, Akeisha? This one's older. Why is the bottom older? That's right. So obviously the strata or the layers on the bottom are older than the ones on the top. Now you could use this. This is how geologists go about figuring out what animal came first and what animal came second and what animal came third. So it's almost like looking back in a book where the pages at the bottom contain fossils that are older than the pages on the top. All right, now let me show you something. You shut this. Courtney, you want to get the lights for a minute? Don't laugh. Cherise, I told you not to laugh. Oh.
Love your pants. Love you.
All right, any idea where I am? Any idea? Well, I don't mean exact. I could tell you the exact location, but the type of landscape I'm on. No, it's not ice, Stephen. Sharice, it's a kind of mountain. I don't know if you can call it a cliff.
It's a rock.
I'm standing on rock. Sharice, got a clue here? Deshante, I'm sorry.
No.
Jaleesa?
Maybe you're standing on a rock and the sediments in the middle are eroded.
No, that's not how this hole got here. All right, Randy. Let me tell you where it was. All right, this is in an island. Does that help? The island of Hawaii. Hawaiian Islands. There's many islands. The biggest one is Hawaii. The one that has the capital, Oahu. Honolulu is on the island of Oahu. But there's something about the Hawaiian Islands. What was that? What's that, Jonathan?
The volcanoes.
That's right. So I'm standing on near the top of a volcano. Now, if I'm standing on the top of a volcano, why am I not standing on sedimentary rock? Why do I have to be standing on another kind of rock that we're going to call non-sedimentary, at least for the time being? Why? Portia.
Because a lot of this probably was.
Can't hear.
Because it was probably hot, the rock or the lava was on it or something.
Well, you're getting close.
Moist.
You're getting close. What is it? What do you say, Chad?
Because at the end of going into the hole, it could probably break off.
No. Wait a minute. We just got through saying, not 10 minutes ago, that if sediments get deposited in some sea and they get buried deep enough, they may be pressed into sedimentary rock. Now, I'm not standing on sediments, and I'm not standing on sedimentary rock. What kind of rock am I standing on? What is that? What do you say there, Keisha? Keisha?
It's standing on non-sedimentary rock.
Yeah, but how is it different than sedimentary rock? Think the way this rock forms. How does it form? How does it form, Thomas? How does it form, Stephen? Heat is necessary. Charisse. What comes out of a volcano? Okay. Now, we can call it lava if it comes to the surface. Some lava never comes to the surface. We can't call it lava, we have to call it magma. Once you say magma, you include the magma that comes to the surface that we call lava, or magma that never makes it to the surface, stays underground. Now look at your charts. What has to happen to magma, or in other words, molten rock, that's where the heat comes in order for it to become solid? Think about it. That's right. So if magma cools, it becomes solid, much the same way that when water cools, it becomes ice. And what kind of rock is this non-sedimentary rock? It doesn't come from sediments. What is it, Thomas?
It's igneous rock.
Very good. So there's another type of rock. Now look at this. Let me lower the screen a minute. So I went down the slope of the volcano. I walked about 4 or 5 miles, and I came to this sign. Sort of giving away my age. What does it say there?
September 1974.
Simidal, what does it say? I know if you could see it, the rest of us could see it.
September 1974, lava flow.
Okay. What kind of rock do you think this is? What kind of rock? Akil. Huh? You're right. Lava is magma. But this long since cooled down. This isn't hot anymore. It's became solidified. What kind of rock? Okay, so let's put that one on the board. If you had to describe how igneous rock is formed, how could you say it in one sentence? One sentence. One sentence. What do you say, Tyrell? One sentence. It's on the chart right in front of you. You see it? Yeah. All right. How does igneous rock form? How does it form, Keisha?
Igneous rock is formed when magma cools.
Can't hear.
Igneous rock is formed when magma cools.
Now, when magma cools, what happens to the state of matter that it's in? There's a change in state of matter. Yeah. So what's the change, Randy?
From liquid to solid.
Okay. So it becomes solid, so we can say it solidifies. There you go. All right, now look at this. What evidence is there that this is igneous rock? Look at the surface. Look at the surface. Look at the surface. Touch it. It's not hot anymore. All right, anyone see any evidence? Remember, it was once liquid. What do you see there? What do you see, Thomas?
It's like the little holes inside of it.
Well, you're right. What do you think the little holes are from? What kind of bubbles?
Magma bubbles or lava bubbles?
Well, what makes bubbles?
Heat and pressure.
Air, some kind of gas. So when this magma came up through the volcano in Hawaii, the magma that it contained had a lot of gas in it. I guess it was something like club soda. Has bubbles in it. So when the rock cooled and solidified, the holes became preserved. All right, now take a look at your chart. I want to show you something. Right under the rock cycle chart is a scheme for igneous rock identification. Now you see where it says vesicular? You see, look where I'm pointing. Vesicular means gas bubbles. So what I'm holding is vesicular basalt. All right, gas bubbles. You could write it right on your chart. All right, now I want to show you something else. All right, I'm going to pass back two igneous rocks. In a way, they're almost the same, and in another way, they're different. Well, that's because it was near the projector. All right, I just want you to look at it and then pass it back. You can touch it, but pass it back, because one of these is a fairly rare rock, and I don't have enough for everybody. Pass it. Okay, I'm going to give one to Akil. All right, now take a look at this. Now, I'll tell you up front that you're looking at igneous rock. Two different samples. Now, if it's igneous rock, where did it come from? All right. Well, yeah. Don't call it lava. Let's call it magma. Okay? Now, let me tell you a little story. Here's a cross-section of some part of the crust of the earth. Now, what do you think these horizontal layers are? What kind of rock? What kind of rock? What kind of rock comes in layers? Yeah, all right? So these are different types of sedimentary rock, the layers. Oldest is on the bottom. Now, what does it say? What does it say here? Keisha, if you can see it, everybody can. Okay, so at one time, this was molten. What happened to at least some of the magma? Look. Well, what happened? What happened, Courtney? That's right. And what we say is it intruded into the rock that was already there. So we call this an igneous intrusion. Sort of intruded into the rock that was already there. Now, let's follow this intrusion. Where did this intrusion wind up?
On the surface.
Okay. Now, that could be a kind of volcano that they have in Hawaii. They're called shield volcanoes because the magma is very liquidy and loose, so it spreads out. Now, why would this magma that came out at the surface cool faster than the magma, let's say, that never made it to the surface? I mean, there's a lot. I'm just using this as an example. Cool slowly. Why? Why is that, Deshante?
Because maybe the air made it cool faster, that's on the surface.
That's exactly right. As a matter of fact, some magma cools even quicker. There's magma, there are volcanoes underwater. And the magma comes up and freezes much quicker than it does in the air. But anyway, how many people have ever made rock candy? All right? The longer you let that string hang in the water, what about the size of the crystal? Did you make it that way? All right, let me show you something. Magma is a liquid. And in a liquid, you have charged atoms. In the 7th grade, you learned that atoms, when they become charged, when they become dissolved, when they became liquid form, when the state of matter changes, they become ions. Now, since this is magma and it's a liquid, the atoms can move around. What do you think's going to be attracted by a positively charged ion? Huh? Why? Right. So given enough time, positive atoms, positive ions attract negative ions or negatively charged atoms, and they'll line up due to electrical charges. Given enough time, they arrange themselves very orderly. And you might wind up with something like this. What is it? That's all a crystal is. It's an orderly arrangement of atoms, and the atoms align themselves when the magma was liquid, when it was in a liquid state. So the longer the magma stays liquid, what can you say about the size of the crystal? Gets bigger. Okay? But suppose the magma comes out at the surface and cools real quick. What's going to happen to the charged atoms? Will they have a chance to line up and become... All right? Now, remember the rocks I passed back. There was one that had big crystals, and there was one that had small crystals. Who has the rock now? All right. Do me a favor, Shauna Lee. Hold up the one that you see has big crystals. Okay, now how do you know it has big crystals?
Because it's kind of sparkly and everything.
Yeah, here it is. Or here it is, I put this down on my floor. No, it's not. You can see that's right, it's granite. All right, so this that cooled on the ground, the crystals had time to line up. The magma took a long time because it cooled very slowly. So you get large crystals. But where the magma comes out at the surface, atoms don't, and magma freezes very quickly. Atoms don't have time to line up. You get small crystals. Okay, now who else has the rock now? Okay, Keisha, hold up the rock that cooled quickly. Hold it up. How do you know that cooled quickly?
It doesn't have a lot of crystals.
Can you see the crystals?
No.
Can you see little specks in there?
Yeah.
Those may be those tiny crystals. All right, now one more thing. If you're wondering how I'm naming these rocks, it's on the chart. First of all, is the rock that you're holding, is it light colored or dark colored?
Light color.
Light color, okay? Now notice on your chart, it says color lights. So these rocks over here are all light in color. Now, according to the chart, what's the color of these igneous rocks? Yeah, it says dark. So since they're light in color, I know, and you should know, that it could be granites, or rhyolites, or even a rock called a pegmatite. Now, look over here where it says grain size. That's a way of describing the crystal size. You might want to write crystals here. All right, which of these correspond to something that has a fine grain or tiny crystals? Look at the measurements. Okay, less than 1 millimeter or less than 1/10 of a centimeter. Light colored, that rock is rhyolites. But if it has bigger crystals, let's say 1/10 or 1 millimeter to 1 centimeter big, that's right, then it's granite. So it's really very simple. Now, if the rock took a real long time to cool, if it's 1 centimeter or 10 millimeters or larger, then it's called a pegmatite. Let me see. Is the pegmatite. Look how big those crystals are. There's one crystal right here. It's feldspar. All right, so this one took a real long time to cool. The crystals are really big. We say it has a very big grain size. Okay, let's wrap this up. How do you know by looking at an igneous rock where the rock cooled, where the magma cooled? What's the general rule, Jaleesa?
Because it has a different type of rock in it.
Look at the rock. How do you know that the magma that formed an igneous rock cooled underground? How do you know, Randy?
Probably because of the size of the crystal.
Okay. So if the magma cools underground, Randy, what did you say?
The size of the crystal.
Well, tell us about the size.
The size.
Big, little?
Big.
Okay. And on the other hand, if the magma came out at the surface, maybe through a volcano, then what's going to be the size of the crystal? Shh, what, Thomas? Okay. All right, now listen to this question. Here's another igneous rock. You see any crystals in here, Edgar? Okay, tiny crystals. What's the name of this rock? Look at your chart. Look at your chart. Here, I got one that was transported by a stream. What's very tiny? Well, it's round. It's really heavy. What's the name of it, Shauna Lee?
Basalt.
Very good. How did you get basalt?
Since Edgar said that it was probably in crystal.
Okay.
I looked at less
So,
than 1 millimeter.
Very good.
And I looked at the dark side.
Ah, ooh, they're dark. Basalt, small, tiny crystals, dark in color. And look, here are the minerals that make up the rock. Here are the minerals that make up granite and rhyolite. Why do you think granite and rhyolite are light in color? What does that tell you about the minerals, the color of the minerals that make it up? What?
It has to be a light color.
Yeah, and look, quartz, clear to white. Feldspar, pink to white. So the rock is white, light colored, because the minerals that make up the rock are light. But on the other hand, different parts of the world have different magmas. It's like soup. So this soup or this magma contained dark ones. Here's a dark green. All right, here's a little bit of black. So now you know how to name the igneous rocks. Now suppose you have an igneous rock that cooled so quickly, no crystals had time to form. What's the name of that rock? I can't pass this around because it happens to be very, very sharp.
Ballistic acid.
That's right. It's glass. If you ever wondered, how did the cavemen shave? How did they shave before they had this? If you hit it the right way, it flakes off and you get something as sharp as a razor blade, even sharper than a razor blade. And that's how they shaved. No, really. I mean, that's how they shave. And another thing is this is one of the items that Indians used as arrowheads and knives. All right? Now here, how'd you know that, Shauna Lee? Where does it say that?
Right? Is that the time?
Okay. No crystals. No crystals tells you something about how fast the magma cooled. Right. So in this case, there's magma that cools so quickly, no ions have time to line up, and you get obsidian if it contains these minerals, or basaltic glass if it contains the darker ones. All right? Now, I sometimes do this. How did the cavemen, or how did the American Indians, people that did, or before they invented or discovered metal, how did they flake these? How do you make a tool out of this? No, they didn't do that. They didn't do that. And they made some very fine tools out of this. I think the Egyptians used this as scalpels. They did operations. So did the Indians in South America. They did operations. They didn't have knives. Well, they had knives, but how do you fashion this into a sharp-edged tool? How? All right? I'm not going to do that. I'm afraid it's going to fly off and hit somebody. But if you hit it just the right way, they use their hands and another tool to bang it on. And if you hit it just the right way, you get these flakes that are real sharp. I think one went into my finger. I feel a little splinter. Clean as a whistle. As sharp as any razor blade. All right, how many people saw the movie Congo? Okay, I didn't see it, my son told me about it. It has to do with diamonds, right? All right, Deshanti, what about the diamonds? Where were they?
There was some cave.
How big were the diamonds?
I don't remember.
All right, I read an article just 2 days ago. They didn't use real diamonds. They didn't use glass. They used the mineral that you find in granite. It's the clear one. It's called quartz. All right? Now, this crystal of quartz is kind of rare because it's called a twin. It has a point on both sides. Not like this one that is only pointed on one side. Now, as far as I know, there's only one place that has these quartz. It's called it's found in the city of Herkimer, New York, and they call it a Herkimer diamond. It's not really a diamond, but it has this shape like a diamond, and that's what they used as diamonds in the movie Congo. All right, now, I told you, we talked about Cooperstown, New York. Remember Cooperstown? Remember Howe Caverns? Right, Howe Caverns? Well, if you go into Howe Caverns to see the limestone cave, right here. Right? I think it's a little north of Albany. If you go a little further north, remember the Baseball Hall of Fame is here, you have the town of Herkimer. And as soon as you get into the town of Herkimer, you see signs, visit the Herkimer diamond mines. And that's what I did. You go to the Herkimer diamond mines, they rent you. Akil, you looking for it? You see it? You can rent hammers, goggles, and they send you out into this cliff, and you can hack away at the rock, and that's how I found this Herkimer diamond. They're there for you to get. Yeah, so it's kind of a neat geology trip. You can go to Howe Caverns, go a little further north, and find mine Herkimer diamonds. I don't think they're found anywhere around the earth, except in Herkimer, New York. All right, now let me ask you, here's a tough question. 634, 28, 6. Okay, how many people saw E.T.? Does that look familiar? That look familiar? This is in Yosemite National Park. It's called Devil's Tower. I believe it's in Yosemite. It's out west. Now this is solid granite. How could you explain, since granite cools underground slowly, that's why it has big crystals, how in the world can this piece of granite be above the surface? What do you think, Portia? Right, this has large crystals. It cooled slowly. It cooled underground. But yet here it is. What do you say, Edgar? What do you say, Chad? What do you say, Courtney? Keisha? No. Stephen?
Maybe since it was underground, maybe it was pushing up on the surface, and the surface just probably cracked and it just came up.
Oh, you mean, what are you saying? It really did cool underground?
Yeah.
All right, so if it cooled underground, that would account for the large crystals. But you see it now above ground. So, what do you say, Jaleesa?
Maybe it cracked the ground and it just kept vibrating.
So you mean something pushed it up?
Yeah.
Okay, that's very good. Almost. It was pushed up, but at one time, it was an intrusion and there was rock around it. What happened to the rock around it? Or what could have happened to the rock around it? And think back to Niagara Falls. Chad.
Went over it and pushed up.
Might have been water what?
Things rubbed against it.
What wore away?
The rock felt different.
Why?
Because it was soft.
Very good. It must have been softer. Okay. Thank you.